So, in the last class we saw that the map f going to integral f dp, where p was a projection valued measure and f was coming from bounded functions on some set omega. We got a, so the map was actually a star homomorphism, which was continuous with norm less than or equal to 1, right. So, the operator norm of f dp, integral f dp is less than or equal to the L infinity norm of f. Okay. So, just to rewind what we were doing, starting from continuous functional calculus, we went into L infinity functional calculus by defining those measures mu u v's, and from the L infinity functional calculus restricting to characteristic functions, we got a projection valued measure which was regular. Now, we are going the other way. To that, we started with a projection valued measure, abstract projection valued measure defined on some space. We proved that the map f going to integral f dp from L infinity functions to bounded operators is a star homomorphism. Okay. Now, we will connect it with the case we were actually doing and see that we can deduce the spectral theorem or versions of spectral theorem from that. Okay. So, let us continue. So, now we return to the case, when omega. So, omega was our space and the sigma algebra was subsets of omega. So, omega is actually sigma. So, if you recall, this was the spectrum of some A, right, where A was a commutative unital C-star algebra. Okay. And well, script f is going to be the Borel sigma algebra. Okay. So, Borel sigma algebra of omega. Okay. So, just to stick to the same notation, omega and script f instead of sigma and script b of omega. Okay. So, that is the only difference here. Now, note that, so just to again to make all the notation consistent and to see that the p u v is actually mu u v, just note that the when I look at p u v e. Okay. So, this is nothing but integral p e sorry inner product of p e acting on u inner product with v, right. So, this was the definition of that measure, which by we know that this is actually integral of omega f d p u v, right. Oh, sorry, not f, that is the chi e, right, chi e. And well, in the specific case we looked at, we had the measure mu, right. So, d mu u v, right. Instead of chi e, we started with f there and then proved that this is a well defined map and we had the algebra property, and then we restricted to chi e and we got p, right. So, in the specific case where you had a commutative unital C-star algebra and the spectrum sigma and Borel sigma algebra of sigma, we went in the other direction, right. Starting from these measures, we defined p, right. So, just to make sure that the notations agree, the p u v now is actually mu u v, right. So, integral of chi e is same as this. Okay. And well, moreover, so remember that this is regular because we got the measure from the Rees representation, right. So, regular because it came from Rees representation theorem. Okay. So, whatever regularity was needed was there, and so the projection valued measure P is also regular, right. That is the definition of regular projection valued measure. So, what we are saying is, if I start with a commutative unital C-star algebra, the projection valued measure we get by going to L infinity functional calculus is actually regular, right. Now, moreover, integral of f dp over omega. So, this is equal to T sub f, right, for f in B sigma, right. So, the B sigma, remember the B is normal B. So, this is bounded functions on sigma, right. If you recall, so let me maybe remind you how we defined T f, right. From continuous functional calculus we jump to L infinity functional calculus by defining T sub f for every f bounded function, right. So, how was it defined? If I look at T f acting on u inner product with v was integral of f d mu u v, right, and this was continuous because I could take the L infinity norm of f, and that gave me a well defined operator because it was a bounded ciscollinear form and all that, right. So, from continuous functional calculus we get these measures mu u v's, and from there we went to L infinity functional calculus which gave us t. But now with our new notation, this is simply f d p u v, and so this is simply integral f d p, right. So, the notations now agree, right. The L infinity functional calculus we get from continuous functional calculus is same as the integral of the function f with respect to the projection valued measures, right. The projection valued measure we got by extending the continuous functional calculus to L infinity functional calculus and looking at indicator functions. Okay. So, that is where we are. In the Gelfand transform notation, in other words, one can also write, in other words, the operator t in A will be integral over sigma t hat dp, right. T hat is the Gelfand transform of t. So, t hat is the Gelfand transform of t, which was a continuous function. So, in particular it is a bounded function. So, I am looking at this, right. So, that will give me t sub f, right. So, t sub t hat which is t, right. So, in our notation that is how it will look like. Okay. So, now we are in a position to write down the spectral theorem. Okay. So, spectral theorem I. So, we will write down two versions, and then of course, there will be other versions which will they are all equal, and we will prove the equivalence also. But let us start with one version. So, this is the projection valued measure version. Okay. But for a commutative unital C-star algebra, okay, we will further restrict to the case of a single normal operator later on. Okay. So, right now it is still slightly general. So, let A be a commutative C-star algebra, C-star subalgebra of B of h with identity, right. So, it is a commutative unital C-star subalgebra of bounded operators on a Hilbert space. Okay. So, A consists of operators. Let sigma be the spectrum of A. Okay. So, that is going to be our notation, and as usual t going to t hat, let t going to t hat be the Gelfand transform, right, be the Gelfand transform, okay, which means, so where is t is in A, right. So, A is identified with continuous functions on the spectrum, right, that is the Gelfand transform, right, and also if I take f, I will have t sub f, right, that is how the Gelfand transform is. Okay, that completely identifies these two algebras. Then there exists a unique regular projection valued measure of course, A is sitting inside B of h, right. So, the projection valued measure is taking values in B of h. Okay. So, I may not say that again and again, but that is understood, right. Projection valued measure P on sigma such that, right, P on sigma meaning. So, sigma comes with the Borel sigma algebra of that set, and the projection valued measure is defined on that, and we have every t in A, the commutative C star subalgebra of B of h is given by an integral, right. So, that is integral over sigma of the Gelfand transform dp, right. So, that is all well defined now, right. So, once you have a projection regular projection valued measure P, we know how to define bounded integral of bounded functions against that, which will give us a bounded operator, right. So, here T hat is a continuous function. So, on a compact house of space, so it is going to be a bounded function, and this integral is well defined from whatever theory we have done in the last 2 lectures, right. And the operator T, any t. So, this is going to be every t for every t in A, right. For every operator in A, I have this integral expression. So, this is one form of spectral theorem. This much we have already proved essentially from all the discussions, right. So, I will just quickly repeat it and then go ahead. Okay. And well, if you want to write the other way, if I take every f in C sigma, that is continuous functions on sigma, I have an operator T sub f, right. So, and so T sub f. So, this is the operator in A, it is going to be the integral of its Gelfand transform, which is f, right. So, that is integral over sigma f dp, right. So, this is true for every f in C sigma, right. So, just writing in different way. Here I took everything in A, here I am taking everything in C sigma, and the same holds for f in bounded functions on sigma, right, bounded measurable functions, right. From once you have this for f in dp, then it extends, right. T sub f will extend to extending from continuous functional calculus to L infinity functional calculus, the same thing will continue. Okay. Moreover, so this much is essentially what we have done so far. So, moreover, let me write down 3 assertions. So, some of it we have already proved. Moreover, so let us write one more line here. If S is a bounded operator, S in B of h, then the following, okay, so I think it is better to write it properly. Moreover, if S is a bounded operator in H, the following are equivalent. The following are equivalent. Okay. So, what are the equivalent statement of which some of this we have already proved. Okay. So, let us write down that S, the operator S commutes with every t in A. Okay. So, S commutes with every operator in A, that is equivalent to S commutes with P e for every E Borel. Okay. So, remember A is identified with continuous functions on sigma. P e, when I look at P e, it comes from the function chi e, which is an L infinity function, need not be continuous. So, these two are sort of different sets, right. So, A is smaller. So, one should keep in mind that the algebra A is smaller and it is contained in integral f dp sigma, where f is a bounded function. Okay. Right. When it is continuous, it goes to A, but the collection of integral f dp's where f is a bounded function is a much larger collection, and PEs are there, not in A, right. 3E. So, S commutes with every T in A is same as S commuting with every projection there, and S commutes with integral over sigma f dp for every f in bounded functions on sigma, right. So, of course, the third one says that S commutes with everything, right. So, we have the continuous functional calculus and then we go to the L infinity functional calculus, look at the corresponding algebra of operators, and if S commutes with that, of course, S will commute with PEs and S will also commute with every T in A, right. So, 3 implying 2 and 1 is trivial, right. So, anyway, let us prove this. Proof. So, quick repeating of what we did so far, so that the star homomorphism property and how we write T as integral over sigma against T hat and dp is clear. Okay. So, let me just quickly repeat that. So, A is contained in B of H. Okay. This is commutative C star algebra with identity. This was the spectrum of A sigma. Okay. For T in A we had T hat, which is a continuous function, that is the Gelfand transform, and the other way, right. For F in C sigma we had T sub f, which is the inverse Gelfand transform, right. This identified both A and C sigma, and for F in C sigma we defined T sub f. Oh, okay. So, the T sub f was defined like this. So, T sub f in A was defined to be T sub f u acting on V equal to integral over sigma f d mu u v, right. Okay, and extended it to, so this is just rewriting what we did all that. Okay, extended to f in bounded functions on sigma, right. That is what we gave us L infinity functional calculus. Okay. So, so we have for f bounded we have this, sorry, inner product of P e acting on u, inner product with V, right, was integral over sigma chi e d mu u v, right, implied. So, this is what we wrote down earlier, P u v e equal to mu u v e. So, I am just making sure that all the notation are consistent. Okay. So, this gave us that T is equal to integral over sigma T hat dp and T sub f equal to integral over sigma f dp for every f in bounded functions of sigma, right. So, that is the first assertion, right. This is just rewriting whatever we had done earlier. Okay. So, there is nothing new here, but just wanted to make sure that everything is all right. Now, we prove the assertion. So, uniqueness of the projection valued measure. So, let us see that there is a uniqueness statement for the projection valued measure, and that follows from the uniqueness of all those measures mu u v's, right. So, let us see. So, the measure P u v, these are regular because these are regular mu u v, and mu u v are unique, right, because it came from the representation theorem. So, the uniqueness of the mu will imply uniqueness of P, right. You can't have another projection valued measure doing this. Okay. So, projection valued measure is unique corresponding to A, right. The script A, once the unital C star subalgebra A is given to you, the projection valued measure is unique. Okay. So, let us prove the assertions. So, now to prove the three equivalences, right. So, the 3 equivalences. So, some of it we already know, let us write down that. So, we clearly, so because the third one is very strong, right. So, clearly 3 implies 1 and 2, right. So, let us go back and see what is 3. 3 is that S commutes with everything, right, integral f dp where f is in bounded functions. Then of course, it will commute with P because P comes from indicator when f is indicator function, and of course, A is contained in this algebra, and if S commutes with the bigger one, then of course, S commutes with A, right. So, 3 implies 1 and 2 is trivial. Okay. And we also proved, so this is something you will have to recall, we also proved that we also proved that 1 implies 3. Okay. So, let us see what is 1. 1 is that S commutes with everything in A, that means S commutes with all the integrals of continuous functions against the projection valued measure. Now, if you recall, we proved some of these results. If f n converges to f p b, right, pointwise and bounded, then integral of f n d p converges to integral of f d p in either in well, we proved that it converges in the strong topology. If we have not, then it converges surely in the weak topology, right, the weak operator topology. But when we started with a commutative C star subalgebra etc., we proved that it converges in the strong operator topology. And so, you can go to any operator which is given by a bounded function, that is integral of f dp where f is bounded, by taking limits from continuous functions. But with continuous functions we already know the commutative property, and so it will 1 will imply 3. So, this is something we have proved. Okay. And 2 implies 3 now is easy, right. So, we need to show that 2 implies 3, that is the standard measure theoretic argument. We are looking at indicator functions, and then you take simple functions and then take the limit, right. So, 2 implies 3. So, we also proved that. Okay. So, 2 implies 3 follows from approximating by simple functions. Okay. So, I will not write down the details here, but what we are seeing is S commuting with P e implies S commutes with integral chi e dp, right, that is what we know. Okay. So, if I take finite linear combinations of chi e, so we will have the same, right. So, so this would imply S commutes with integral over omega f dp for every f simple, right. But then if I take an L infinity function f bounded function, then it is the limit of simple functions and limit in the supremum norm, and then you know that the integrals also converge in the operator norm, right, and then S commutes with the simple functions. So, that will tell me that at each n level. So, S integral f n dp equal to integral f n dp s, and so by taking limit I will get the result for f bounded, right. So, this implies that S commutes with integral over omega f dp for every f bounded. Okay. So, that proves the 3 assertions we had. Okay. So, next, so this is one version of spectral theorem. So, let us go back to understand this. So, it is written in the in this form. Okay. So, if I take a commutative C star subalgebra with identity, which is just operators, right, consisting of operators, then each operator can be written as an integral of its Gelfand transform against a unique regular projection valued measure. Okay. So, the projection valued measure is a unique regular projection valued measure, and it comes from extending the continuous functional calculus we had earlier to L infinity functional calculus. Okay. So, that is the trajectory we have taken. We will have other versions of the spectral theorem, because this is a slightly abstract version. Sometimes this helps, sometimes there are other versions which will help, which is realizing the algebra of operators as multiplication operators on an L2 space. what the price we pay is there are certain non uniqueness factors that will come in, okay. But it is still easy to deal with multiplication operators on some L2 space, L2 measure space, because these are much more concrete, and we will see that sometimes that helps, okay. So, let me try to write down that as well. So, next we will see how to realize A as a as multiplication operators, okay. So, as multiplication operators on some L2 space, okay, on L2 spaces. Okay, that is a much more concrete way of realizing it, except that we lose some uniqueness property. So, let me use some definition here, because what sort of measure space are we getting is important, right. So, so omega f mu. So, omega is some set, f is a sigma algebra of subsets of omega, mu is some measure, okay, be a measure space. So, the mu here is a positive measure, okay. Then it is called a semi-finite, okay, not sigma finite, semi-finite measure space. If for every E in F, so for every measurable set E with mu of E equal to infinity. So, any set which has infinite measure has a subset which has finite measure, okay. So, positive finite measure, okay. So, mu E equal to infinity, there exists F in script F contained in E such that 0 strictly less than mu of F strictly less than infinity, okay. So, I can find a measurable subset of the set E which has finite measure, not 0, but positive measure, but finite. So, such a thing is called a semi-finite measure space. So, let us have a lemma just to see what multiplication operators do here. Let omega script f mu, after that we will be able to write down the spectral theorem version 2, okay. So, let omega f mu be a semi-finite measure space, for phi in L infinity of mu, right. So, I take a bounded measurable function on omega phi, define let us say m phi. So, this is the multiplication operator, that is multiplication by phi. So, m phi from L2 mu to L2 mu. So, this is going to be a bounded operator, simply multiplication by phi, right. So, f going to so maybe let me write it in terms of m phi itself. So, m phi of f should be phi times f, right. So, that is a bounded operator, and clearly the norm is less than or equal to the L infinity norm of phi, right. So, the assertion is then the operator norm of the operator m phi multiplication by phi is equal to the L infinity norm of phi. So, let us quickly prove that, and then we will stop for this time and then continue with the spectral version, spectral theorem version multiplication operator in the next class. Okay. So, let us prove this clearly. So, I look at m phi and look at the operator norm of m phi, right. So, I look at m phi f and then I look at the L2 norm. Well, what is this? This is phi times f modulus square d mu. Of course, this is less than or equal to the L infinity norm of phi and then L2 norm of f, right. So, this implies that the operator norm of m phi, this is the trivial part, right. So, this is less than, sorry, operator norm is less than or equal to the L infinity norm of phi. Okay. Now, we use the semi-finiteness part. Okay. So, let for epsilon positive, let take a set E x in omega such that modulus of phi of x is greater than L infinity norm of phi minus epsilon. So, the moment you reduce from L infinity norm of phi, the set where phi of x has modulus greater than L infinity norm of phi minus epsilon, right. So, something smaller than L infinity norm, that set will have measure positive, right. Then the measure of E is positive. Of course, the measure may be infinite, that is where we use the semi-finiteness property. Okay. So, if m mu E is infinite, so if the set has infinite measure, it need not, if it has finite measure, the set itself will work, otherwise you can choose a subset, right. So, that is because of semi-finiteness. So, choose f contained in E such that it has positive measure, but strictly finite, right. So, less than infinity. So, strictly finite measure. Well, what is the advantage of that? So, then if I look at the characteristic function or indicator function of f, since it has finite measure, it is going to an element in L2, right. So, I can apply m phi on it. Okay. So, hence if I look at m phi acting on this function chi e, well, this by definition is chi times phi times chi e, right. So, let us look at the norm of this. So, L2 norm square, let us say m phi of chi not E, sorry, f, right, because we need it to be in L2. So, why do I have E here? It should have f there. So, chi f and chi f, right. So, m phi acting on chi f is L2 norm square is equal to mod phi square, right. But chi f square is simply chi f. So, I am integrating over f d mu, but f is contained in E, right, and E is this set. E is the set where mod phi x is greater than something, right. So, this is greater than or equal to L infinity norm of phi minus epsilon whole square, right, times the measure of f. Now, the measure of f is positive and finite, right. So, there is no problem. So, this is a non-zero L2 function and I have the operator acting on some vector is greater than or equal to some constant times the norm of the vector, right. So, this is the norm square of the vector, remember that L2. Okay. So, this implies that the operator norm of m phi, it should be the operator norm, keep writing L infinity, is greater than or equal to the L infinity norm of phi minus epsilon, right, and this is true for every epsilon, implies the operator norm. I know that it is already less than or equal to L infinity norm of phi equal to L infinity norm, right. So, whenever I have a semi-finite measure space, the operator norm of a multiplication by L infinity function is actually the L infinity norm of phi. Okay. So, we will stop here and we will continue in the next lecture by going to the spectral theorem which is written in terms of multiplication operators. Okay. So, instead of realizing the algebra of operators as integral against projection valued measures, we will try to realize them as multiplication operators by bounded functions on L2 spaces. So, that is the next version of the spectral theorem. Okay. So, we will stop here.